Okay, good morning to all of you. I welcomes to all in our lecture series on mathematical physics, that is your core paper 5, belongs to third semester BSc Physics honor syllabus. In this class we are going to discuss to solve the Laplace equation in two dimension, that is your del square u by del x square plus del square u by del y square equal to 0 in a rectangular plane. Here it has been given the boundary conditions are ux0 equal to 0, that means y, when y equal to 0, that will be 0, uxb equal to 0, u0 y equal to 0, and uay equal to f of y. And we are going to solve this differential equation, partial differential equation, or you can say Laplace equation in 2D by using separation variable method. Separation variable method. Okay. In our last class, we have been discussed in detail solution of Laplace equation by separation variable method, but here this is in your 3D Cartesian coordinate system. But whatever we are going to discuss in this class, that is your 2D. Okay. So let's start. Here the given 2D Laplace equation is your del square u by del x square plus del square u by del y square equal to 0. Let that is your equation number 1, and the given boundary conditions are these. These are the given boundary conditions. 4 boundary conditions has been given. So these are 4 boundary conditions. Here it has been given. These are the 4 boundary conditions. Okay. From equation number 1, here it can be found that u is the function of x and y. See, here del square u by del x square, del square u by del y square is there. So here this function u have the two variables that are x and y. Okay. Or you can say that u is the function having two independent variables, that is your x and y. So u is the function of uxy. Let this is your equation number 2. Now consider the general solution of the equation number 1. Equation number 1 is by considering SVM. See, if we are going to consider SVM, the method that your separation variable method, the first step that we have to consider the general solution of a partial differential equation like this way. Separately we have to separate the different functions of the main function. So here u is the function of xy, and it is written in this format, separated by two different functions x and y. Here x, capital X is the only function of x, capital Y is the only function of y. So here uxy, solution of the differential equation, let consider the general solution, let consider x into y, capital X into y. Let this is your equation number 3. This is the we are following the steps, okay, or the procedures, whatever we are discussed in our initial classes. You can follow those videos. Okay. Now del square u by del x square. Here if we are going to consider del square u by del x square, considering equation number 3, then here y is the constant. So y into del square x by del x square. Let this is your equation number 4. Likewise del square u by del y square, considering equation number 3, we can get x into del square y by del y square. Let this is your equation number 5. See, whenever we are considering the derivative with respect to y, here capital X is constant. Whenever we are considering derivative with respect to x, the capital Y is the constant. So here we found 4 and 5 from equation number 3, right? Now we have to put 4 and 5 in equation number 1 here, and here we got y into del square capital X by del small x square plus capital X into del square capital Y by del small y square equal to 0. Now we have to divide x into y with above equation. With this equation we have to divide xy. What we are going to get, see, we are following the steps, okay, procedures, whatever we have discussed in our first class of your separation variable method. You can follow that video. So by dividing xy, what we are going to get, we have to go to the next page. Here y by xy del square x by del x square plus x by xy del square y by del y square equal to 0. So y got cancel, x got cancel. We found 1 by x into del square x by del x square plus 1 by y into del square y by del y square equal to 0. That implies this term, which is function of only y, taken right hand side. So 1 by x into del square x by del x square equal to minus 1 by y into del square y capital Y. This is capital Y, okay, by del y square. Let these two terms, this is your term belongs to only function of x, this is your function of y. If both are equal, let both are equal to another constant k square. Let, or say, that is your k square, right? Now this will be equal to k square and this will be equal to k square. Let this is your equation number 6 and 7. Now here you can see that this equation will be del square x by del x square. Just multiply x with a k square and taken this side, k square x equal to 0. Now the auxiliary equation of this second order differential equation will be how much? M square minus k square equal to 0. Okay, here m we know that d by dx. So as here d square by dx square is there, or del by del x, m equal del by del x. Okay, so del square by del x square is nothing but m square. Okay, so here m square, here for this second order differential equation, auxiliary equation will be m square minus k square equal to 0 and m equal to plus or minus k. So here we found the two roots. So if two roots, then the solution will be how much? Solution will be a e to the power kx. This can be one solution. Suppose we are going to consider x1 is your solution. x1 equal to a e to the kx and x2 equal to b e to the minus kx. That means these two solutions are solutions of this differential equation. Now if we are going to consider superposition principle, addition of this linear superposition principle, then addition of these two solutions will be the solution of the differential equation. That means if we are going to consider x equal to addition of these two separate solutions, that is your x equal to a e to the kx plus b into e to the minus kx will be the so-called general solution of the equation number 6. Okay, this is your equation number 6. Right? Now we have to consider this one, minus 1 by y into del square y by del y square equal to k square. So it will be del square y by del y square plus k square y equal to 0, right? So here you can see that the auxiliary equation of this second order differential equation will be how much? M square plus K square equal to 0. Okay, so M equal to K square gone this side, it will be minus K square, root over of minus K square will be plus or minus Ik. So here the two roots also we got from the auxiliary equation. Likewise, y1 will be the solution, that is your c1 e to the power I ky. Okay, y2 will be another solution, that will be constant, some constant d1 e to the power minus I ky. These are the two separate solutions of this differential equation. You can try by your rough, in your rough you can try by considering this one, it will be solve this one. This solution also will be the solution of this differential equation. You can try in your rough, no problem. And by considering linear superposition principle, then addition of these two solutions, like y will be equal to c1 e to the iky plus d1 e to the minus iky. This will be also the solution of this differential equation 7. Okay, also the differential equations are 7. Now we have to consider the further simplification, that e to the power iky can be written as cos ky plus I sin ky. E to the power minus iky can be written as cos ky minus I sin ky, right? So here you can see that c1 cos ky, d1 cos ky. So cos ky, if we are going to take common, we can found c1 plus d1, right? So c1 plus d1 considered as c, right? Here you can see that c1 i1, d1 c1 i1, c1 I, here you just consider this term c1 I and minus d1 I. If I will take common sin y from those two terms, we can get c1 I minus d1 I into sin y. Okay, into sin y. So here instead of writing c1 I minus d1 I written d sin y, right? So here d represents the constant, that is your c1 I minus d1 I, and c represents your c1 plus d1. Okay, okay, now we have to put this solution, that is your equation number 8 and equation number 9 in equation number 3. Equation number 3 is your general solution, that is your u xy equal to x into y. Okay, now u xy, the general solution will be how much? You can see the general solution after substituting 8 and 9 value in equation number 3, we get the general solution will be uxy equal to a e to the power kx plus b e to the power minus kx into c, this one c cos ky plus d sin ky. Let this is your equation number 10. So this is your solution or general solution of the given second two-dimensional Laplace equation. But we have to substitute, or we are going to consider the boundary conditions to find out these constants. Okay, so half portion of the derivation has been completed. Then we are going to go for the boundary condition. So here in our last page we found this is your equation number 10. Now we have to use the boundary conditions. Why? We have to find out the constants. For that we have to use the boundary condition. So first boundary condition, I is the first boundary condition, is your u x0 equal to 0. That means we have to put instead of y equal to 0, and if we are going to put y equal to 0, this side this will be cos 0 equal to 1, this side it will be sin 0 will be 0. So this term will be 0, and here x term is there as usual. It will be like this: a e to the kx plus b e to the minus kx, right? By substituting 0 here, this term will be 0 and this term will be 1c, and it will be equal to 0 because u x0 equal to 0, it has been given as our first boundary condition. You can see this is your first boundary condition, right? Now here you can see, here we have been considered the first boundary condition, and in that first boundary condition we have been used that y equal to 0. That means we have been tailored, changed the y value. So here in the right hand side of your equation number 10, you can see that the y values are present here and here. So that means we are trying to change this term and this term. So whenever we are trying to change this term and this term with the help of the first boundary condition, that means we are intent to find out the constant c and d, right? So this will be keep constant, and we are going to consider c equal to 0. See, by considering boundary condition this one, we found 0 equal to this into this. So as we intend to find out the constant, and here in the first, by considering first boundary condition, we change the y, then from this equation we have to consider c equal to 0, not a e to the kx plus b e to the minus kx. You got my point? So again, so as we are changes the y value, so this term and this term we want to find out the term, the constants c and d is going to be find out, not this one. Okay, so here I have written that a e to the kx plus b e to the minus kx not equal to 0. If we consider this one, otherwise in this way also you can understand that here if we are going to consider this will be equal to 0 to satisfy this equation, if we are going to consider this will be equal to 0, then if we have to put 0 here, the entire solution is going to be vanished, right? So hence c will be equal to 0. So two things you have to remember here: what you changes, why you have been changes. So you have to intend to find out c or d term. C and d constant you intend to find out, not this one. Or you can consider that if you are going to consider this will be 0 to satisfy this equation, then entire general solution will be 0, because if I am going to put 0 over here, then solution has been vanished. So we have to consider c equal to 0, not this one. Okay, now if c will be 0, then the equation number 10, here you put c equal to 0, then the equation number 10 will be how much? A to the kx plus b to the minus kx. This term has been vanished. So d sine ky equal to d sine ky, which is considered as equation number 11. Now we have to consider boundary condition 2. The boundary condition 2 has been given that u xb equal to 0. So here the recent final general solution is our equation number 11. So second boundary condition is going to be apply on this one, right? So you just apply. So xb, uxb means wherever the y will be there, we have to put b. So here a e to the kx, b e to the minus kx, nothing changed, into d sine k, instead of y what we have to put? B, and will be equal to 0, because condition is that xb, uxb will be 0. So 0. So here what we done, we changes y value. That means we tailored this term, we not tailored this one. If we are tailoring this one, that means we are intent to find out the constant d, right? So this not to be 0, this not to be 0. Hence d sin kb equal to 0. Okay, or you can consider in this way that if this will be considered as 0, if I will put 0 over here, then 11, equation number 11 is going to be vanish. So to satisfy this equation, this equation, we can consider this will be 0 or this will be 0, but this could not be considered as 0. By two way you have to, you can understand that if this will be 0, then entire this is going to be vanish. Okay, so this has to be taken as 0, but with some condition. Okay, sorry, this is going to be considered as 0, but with some condition that we are going to discuss. Or either way you have to understand that here you have been tailored this term by considering y equal to b. So you are not going to be bothered that this term has to be 0. So this term not to be 0, this term you have to consider as 0 to satisfy this one, to satisfy this equation, right? So if we consider that d sin kb equal to 0, here in this case d could not be 0 because d is a constant. And if we are going to consider d will be 0, you just put d will be 0 means here entire 11 equation also vanished. So d could not be considered as 0. Then what we are going to consider the 0? Sin kb equal to 0, right? So if sin kb equal to 0, then kb equal to n pi and k equal to n pi by b. So this is the condition what I told. Okay, so here what I told that this is going to be considered as 0 with some condition, that is your k equal to n pi by b, right? So now if we are going to consider this one, then modified general solution or modified equation number 11 will be how much? This one, uxy equal to a e to the kx plus b e to the minus kx into d sin n pi y by b. Instead of k, this one, instead of k, what we have to write? N pi by b. So n pi by b into y. Let this is your equation number 12. Then we have to consider third boundary condition. So this is our equation number 12, whatever written in the last page. So now we have to consider the boundary condition. So as per the boundary condition, when x equal to 0, the uxy equal to 0. Okay, now we have to use this boundary condition on our modified general solution. This is the latest modified general solution by considering last two boundary conditions. Okay, so here we have to use or going to apply this boundary condition. Okay, so for only for that it is written 0 for equation number 12. We get that implies u 0y will be equal to 0 a plus b. How it will be a plus b? You can see e to the power 0. X instead of x we are going to consider 0, no? So it will be e to the power 0 will be 1, e to the power 0 also 1. So a plus b into d sin n pi y by b, right? So here, as I told, what value we have been tailored? We have been tailored the x value. So x value you can found in this term. That means you are intent to find out a and b. So in this equation we can consider a plus b equal to 0 or this will be equal to 0. But as we intend to find out a and b by tailoring the x value, so a plus b is going to be considered as 0, right? So a equal to minus b, Now the equation number 12. Equation number 12 we have to put instead of b equal to minus a, right? So if it will be minus a, this will be a e to the kx minus a into e to the minus kx. So a taken outside, e to the power kx minus e to the minus kx into this one d sine n pi y by b, right? Or we can write uxy equal to 2a 2 multiplied 2 divided, okay, e to the power kx into e to the minus kx by 2 into d sine n pi y by b. So here this much value is nothing but sine hyperbolic kx, that we know very well, okay. So uxy will be equal to 2a sine h kx into d sine n pi y by b, okay. So we found that uxy equal to 2a sine h kx into d sine n pi y by b. Here n equal to 1, 2, 3 and so on. Okay, so whenever we are going to consider n equal to 1, it will give one solution. Whenever we are going to consider 2, another solution, 3, another solution. But n not to be 0. If I put n equal to 0, then entire solution is going to be vanished, right? So as uxy depends solely upon the n, so and for each and every n value it is giving one solution. So in general we can write unx equal to an sine h n pi x by b into sine n pi y by b. Here n pi by b, how it is came? You can see instead of k we have been written n pi by b. Already k value we found previously, right? This is your k value. I just substituted there. K value has been substituted here, n pi by b, okay. Now here n number of solutions, okay. Here you can see that an is considered as 2a into d. An is nothing but 2a into d. So here n, from this equation 13 you can find n number of solutions. For each n value you can found one solution, okay. But according to superposition principle, whatever we have been discussed here, that if one differential equation has two solutions, then the linear combination of these two solutions will be the solution of this differential equation. Likewise, here we found the number of solutions when the n is going to be 1, 2, 3 like this. So their superpositions of the solutions will be also a solution, will be the solution of that differential equation. So here when n changes from 1 to 3, we are going to get new solutions. So we are going to consider the superposition principle, and we can get the general solution is uxy will be summation over n unx. That means this is telling that u1 plus u2 plus u3 and so on, right? So I not written these things, it can be perceived easily, no problem. So summation over n un xy, this is nothing but the, by considering superposition principle, or this is nothing but addition of the solutions for each and every n, right? So here unxy will be summation over n equal to 1 to infinity an sine h n pi x by b into sine n pi y by b. Let this is your equation number 14. This is your general solution. Right? Now we have to use the fourth boundary condition. Then another boundary condition it has been given. You can see up to this much we have been used our three boundary conditions. The last boundary condition is this one, uay equal to fy. You can see that uay equal to fy, that we have to use, and we are going to get the final solution. See, now we have to use fourth boundary condition, that is your IV, uay equal to fy. That means instead of x we have to put y, sorry, a. So where we have to put? We have to put in the latest solution. Latest solution is nothing but your 14. Here we have to put. So uay will be here n pi a by b sine, here only x is here only going to be changed as a. So uay will be equal to fy equal to summation over n equal to 1 to infinity an sine h n pi, instead of x we have to write a by b into sine n pi y by b. Let this is your equation number 15. Then further simplification whatever we have, that has been considered the Fourier series concept. How it is? You can see that the equation 15 can be written as, here you can see this equation can be written as uay equal to fy is equal to summation over n equal to 1 to infinity bn sine n pi y by b. So here bn is nothing but this much. This is a constant. An sine h n pi a by b is considered as bn. Okay, and this term is here. Let this is your equation number 16. You can see that this is looks like your Fourier sine series, right? Only sine terms are there. b1 sine pi y by b plus b2, like that. It is looks like Fourier sine series. But as per the boundary condition, we can found y varies from 0 to b. Here you can see that boundary condition, here in your boundary condition, y varies only from 0 to b. 0 is your lower limit of y and upper limit is your b. Okay, y, that means y varies from 0 to b. Okay, then what is going to happen, we have to see. So but we know that fx equal to 0 to n equal to 0 to infinity bn sine n pi x by l is the Fourier sine series where x varies from minus l to plus l. You got my point? Here this equation, you follow this equation and this equation exactly same, but here this L varies from minus L to plus L, then we can say that this is nothing but is your Fourier sine series. But here sine n pi y by b, this b varies from only from 0 to b from the boundary condition whatever we found. So then is this series will be called as the Fourier sine series or not, that we are going to be further going to be discussed. Okay, but here y varies from 0 to b, whatever what we discussed. Hence equation number 16, this one, equation number 16 is called as Fourier half range sine series of fy in the interval 0 to b. If suppose if y varies minus b to b, then the equation number 16 will be called as your Fourier sine series. But here as b varies from 0 to b, you can see if minus b, from minus b to b, if it will vary, your y is going to vary from minus b to b, then it will be called as Fourier sine series. But however it is varies half portion only for that, the equation number 16 will be called as Fourier half range sine series of fy in the interval 0 to b, where Bn will be written as 2 by b 0 to b fy into sine n pi y by b into dy, right? Or an into sine h into n pi by a equal to how much? Will be this much, because this constant has been considered as bn. See, in equation number 15, this constant is there, and in equation number 16, instead of this we have been written bn. So if bn will be this much, obviously an into sine h n pi a by b will be also this much. Okay, so that implies an will be equal to, just this one is divided in the right hand side, so 2 by b into this much sine h n pi a by b into this integration. Let this is your equation number 17. So here n equal to 1 2 3, and for each n value we can evaluate a1 a2 a3 n values by using equation number 17, and put in the general equation or solution equation number 14. So this is your equation number 14. So by considering equation number 17, we can found a1 a2 a3 the constant values, right? And we have to put over here in this equation number 14. Okay, so if I will expand this one, it will be a1 sine h pi x by b sine pi y by b. Wait, that means whenever you are going to be expand this one, you can found a1 sine pi x by b into sine pi y by b plus a2 sine h 2 pi x by b into sine 2 pi y by b, and so on. And these constants a1 a2 then a3 these constants can be evaluated with the help of the equation number 17. So using equation number 17, we can evaluate the a1 a2 a3 constants, and we are going to be substitute here. This is your uxy, the general solution. Okay, so put in the general solution or equation number 14, that is your un xy n equal to 1 to infinity an sine h n pi x by b into sine n pi y by b. Okay, so here you can see that the general solution will be a1 sine h pi x by b into sine n pi y by b plus a2 sine h 2 pi x by b into sine 2 pi y by b, a3 sine h 3 pi x by b into sine 3 pi y by b, and so on. This will be the general solution, or you can write this one will be the general solution of the Laplace equation in 2 dimension, or you can say in rectangular plane, having these boundary conditions. So if there is if we do not have any boundary condition, then you are going to get this is your general solution. So with the help of the boundary condition, we found the general solution is this one, or you can write this one. Okay, so I suggest watch carefully this video, write down the note, and ready for the next class. We are going to discuss solution of Laplace equation in cylindrical coordinates. Okay, so thank you so much for watching this video. Thank you.